Okay, LeetCode 21, merge two sorted lists. This is grind 75 number 3, I think. And in this problem, you're given two sorted lists and you want to merge them together such that the result is also sorted. So how do we do that? Well, there are two approaches. The first one is a recursive approach, which I think is pretty easy once you see the code. It's kind of hard to explain, I feel like, but within itself, like it itself is pretty easy. The other way is to do an iterative approach. And I think it's a little bit trickier. Some people even say that the iterative approach itself is like a medium problem. But we'll see. So this is going to be the recursive approach right here. As with all recursive problems, you need a base case. And so I think the base case, we can just say like we have something like this. We have a node here, but we don't have a node here, or vice versa. We don't have a node here, or we have a node here, right? And in either case, we return the opposite of the one, which is null. And you might be wondering, well, what don't we have a case where, both are null? And you're right, that can happen, but this will take care of it on its own. And this is how it will happen. So let's say we have both are null. If both are null, let's say this is the first thing that I reach in my recursion. So I say, well, I see that list 2 node is null. Return the opposite of that. That one's also going to be null. So I'm going to return another null, right? So it's kind of redundant. So it's equivalent. This is just doing the work of essentially just saying if not L1 and not L2, return null, right? It's just doing that. So that's pretty much all there is for the base case. As for the recursive step, what do we do here? Well, for the recursive step, we just need some logic. We just need to check, is one of the nodes less than the other one? And if that node is less than that other node, the smaller of the nodes gets to make a connection, right? And the recursive part comes in where the connection that that node makes has to follow the same logic that was applied earlier. And the logic in this case being, hey, is this node less than this node or vice versa? So let me draw it out. All recursive problems have a call stack, right? A mistake that people sometimes make is they have a recursive solution and say, oh, it's just O of 1 in terms of space, but you have an implicit stack that's defined for you whenever you do a recursion. So we'll call this stack S. So when my program is first called, these are the two heads of my thing, right? And so I compare 1 and 1, and I see that they're equal. And so in my case, I say, well, if two things are equal or greater than, L2 is going to be the one that gets to make a connection, right? So L2 is going to get to move forward here. So L2 is going to get to map to something, but you can imagine it as being written like this. It would be like L2 dot next is going to equal to like our recursive call. And what gets passed into this recursive call? Well, it's going to be L2.next itself, right? Because we don't want to analyze the same node twice, right? We just checked 1 and 1, right? We decide that this node was going to be a candidate to map to something else, so we don't have to check it again. But we did not take this node with us, so we're going to take it into our recursive call again just to check. So this is how it's going to look. The recursive call is going to be made like this. So we're going to have a stack. So the first call is going to be, we're going to pass in 1, and we're going to pass in 3. So we're going to do that, right? And right here, since we decided that 1 is going to be the one that gets to map to something, I'll just leave it here, right? And I'll just have like a bunch of question marks that will represent our the recursive calls. So they'll go like this. And I think there should be one more, maybe. Okay, we'll just keep this going like this. We'll just say it's a chain of unknowns. So we have one maps to something, right? But then one itself makes another recursive call. So we get to see here. It gets to make this call right here, 1 and 3. Well, we see that 1 is smaller. So 1 now becomes a candidate to make the recursive call now. It becomes a candidate for making a connection. So we pass in 2 because we don't want to analyze 1 again. And then we keep 3, right? Close this out. Okay, next we're comparing 2 and 3. We see that 2 again is smaller than 3. So 2 gets to connect to something, but we don't want to analyze 2 again. So we pass in the next of 2. So we pass in 4. And then we keep looking at 3. Right? Awesome. Then we have 4 and 3. Well, 3 is smaller this time. So 3 gets to make a connection. And so what does that pass? What does 3 connect to? Well, 3 connects to its own next, which is 4. And the current L1 value, which is also 4. So let's close this up. And then there's going to be another call. We have 4 and 4. So we see 4 is equal to 4. So we take the case where we let L2 make a connection. And since L2 is making a connection, we don't send in 4, we send in the next thing of 4. But we see here that 4 just maps to null. So we send in a null here into this call, and we pass in 4 right here. Okay, cool. But we recognize that as we discussed earlier, this is a base case. So this is just going to return 4 because the opposite of the null is the not null, which is the 4. In this case, we see, let me use another color. In this case, we see that 4 gets to get returned. In this case, we see 3 smaller. So 3 gets to get returned. In this case, we see that 2 is smaller, so 2 gets to get returned. In this case, we see 1 smaller, so 1 gets to get returned. Now remember, this is the very first recursive call we made back when we checked these two, right? Back when we checked these two, that was the first recursive call we made. And we decided that 1 was going to be the one that makes the next connection, right? So we go down here. So we say, well, 1 now gets to connect. So 1 gets to connect to 1, right? Right here, this one right here. Then it gets to connect to 2, right? Then it gets to connect to 3 right here. Oops, sorry. Let me zoom back in. It gets to connect to 3. Then it gets to connect to 4. And then finally, it gets to connect to 4 again. And we have our sorted list. So we have 1, 1, 2, 3, 4, 4. And let's see if that's equal to the result here. 1, 1, 2, 3, 4, 4. It is. Cool, right? So this is how it looks. It's very trippy to visualize because you're trying to like draw out the call stack. And once you see the code, you'll see it's actually kind of trivial. And I think these problems actually might be better to just tackle first instead of drawing first, now that I think about it. But let's see. Okay. So as we talked about the base cases, if there's no list 1, I'm going to return list 2, right? Otherwise, if there's no list 2, we're going to return list 1. right? That's pretty easy. Next, if list1, if the value at list1, if it's less than list2 value, well, we know that we want to use list1 as a candidate to make a next connection, right? Because it's less than list2. It's the smaller one. So we're trying to preserve that ascending order. So we say, well, list1 next is going to equal to merge two lists. And we said that earlier we said that, well, we don't want to pass in just list1, right? Because we already examined list1 and its value. We don't want to examine it twice. We don't want to make that mistake. So what we do is we pass in a list1 next, and we compare it to whatever we left behind with list2, because we didn't pick list2 as a candidate to make the next connection. We picked list1. So we just pass in list2 as is. After this, of course, when this is done, we'll return list1 just to update it. Else, right? This is the case where list2 was less than or equal to list1. So it's the opposite of the first one. We do list2 next. So list2 was picked as a candidate to make the next connection. We say merge two lists. We say list1. So list1 didn't get picked. It gets passed in as is. And then list2 next gets passed in because we don't want to reuse list2 again because, right, we just examined the list2 and its value. So we don't want to examine it again in the next recursive call. So we do that and we return list2 and let's run it. Let's see what happens. As you see, it works. We can submit it. There we go. It's pretty fast. The runtime of this is O of n, right? Because at most, well, it would be O of m plus n because we're going through all of this. The space complexity, though, since we have this implicit stack, would be linear, right? It wouldn't be constant, it would be linear. And this is where the iterative solution comes in. So the iterative solution allows us to do this same thing in linear time, but also in constant space. So let's delete and let's look at our iterative solution. So let's do the same thing here. Let's draw our nodes. So do 1 maps to 2 maps to 4. And for the other color, we do 1 maps to 3 maps to 4 maps to 5 maps to 6. And I just want to show this because there's going to be something tricky we have to do with this implementation, and I want to immediately get this case out of the way. So what we do is we're going to initiate ourselves a temporary head with like some random value. We can just pick like -1. Cool. And then we're going to have a pointer to this. It's going to be called previous. So this is going to point to the previous thing that we accessed. So it's going to start out pointing to the to this temporary head. And then we're going to have our L1 pointer, and we're going to have our L2 pointer corresponding, starting out at the heads of the lists. And this is what we're going to do. We're going to make a comparison. So we're going to say, okay, compare this and this. Compare the things that the two pointers are pointing at. Well, we see that L2 is equal to L1. So just like in our recursive solution, we say, okay, well, L2 should be the thing that gets to make a connection. Except in this case, we're going to say L2 is the one that gets connected to. So we do a connection like this. So we connect it up here. And since L2 just got connected to, we don't want to check it again. So we move L2 forward and we move previous to this because this is technically now our previous, the previous thing that we visited and connected. So we go here and now we do a check again. We see, okay, we'll compare L1 and compare L2. All right, so we're comparing these two things right here. which one's smaller? Well, 1 is smaller than 3, so that means previous gets to connect to L1. And since L1 just got connected to, L1 gets to move forward. Okay, and previous, as always, moves to the previous thing that was just accessed, which was this. Again, L1 and L2 get checked. We see that L1 is less because value is 2. So previous makes a connection to L1. And since L1 just got connected to, L1 moves. Cool. And then previous moves as well because that's the last thing they just got linked to. So we do that. And now we check again. We see, okay, which one's smaller? Is L1 smaller than L2? No, L2 is 3, L1 is 4. So we do a connection from previous to L2. And since L2 just got connected to, L2 gets to move. Previous gets to move here, the last thing it was pointing to, or the last thing that got accessed. And then we do the comparison again. 4 and 4 are the same. So we see that. And so that means by our rules, I'm just going to automatically connect. In the case that both are the same, I'll just connect to this. Since this just got connected to, L2 is going to get to move forward. Previous is going to get to move to the last thing that's connected. And we do the check over again. So we see L1 is 4 and L2 is 5. Well, what's smaller? Well, 4 is smaller than 5. So previous gets to connect to L1. Now L1 is not visualized, but L1, the next of L1 points to a null. So since L1 just got connected to, I'm going to move my L1 pointer, and that's going to be pointing to null. I'm going to also move my previous pointer, and I'm going to move it here. Now, pretty much from here though, we're done. We just have to do one more check because one of our pointers reached null, and we know since both lists are sorted, I can just connect the one that's currently. I can connect previous to the one that's not null anymore, right? So I know that L1 is null now. So since L1 is null, previous.next now gets to connect to just L2. And I can just pretty much stop here, right? Because if we follow our blue arrows, we see we go from our dummy head to 1, to 1, to 2, to 3, to 4, to 4, to 5, to 6. And that's sorted. The last step that we'd probably want to do is we would want to go in here and you want to sever this connection and just return dummy head or temp head.next. And you're going to have your sorted merged linked list. Okay, let's try to write this out. So basically what we're going to do is we're going to have a list node temp is going to equal to new list node, and we'll say like -1. Then we're going to have a list node called previous, and I forgot these should be pointers. And we're going to have previous, and that's just going to equal to temp. And then basically we're going to do while L1 and L2. So both of these are not null. We're basically going to do this. So we're going to ask if L1 value, and I noticed that it's list1 in this scenario. I called it L1 in my drawing. We have list2. So we have if list1 value, if it's less than list2 value, what's going to happen, as in our picture, we're going to connect previous. So we're going to say previous next is going to equal to list1, right? So we're going to do that. And then what we're going to do is since list1 is the one that just got connected to, we're going to say list1 is going to equal to list one next. Otherwise, else, we're going to say, okay, well, in this case, a list 2 is going to be less than or equal to list 1. So in that case, previous next is going to equal to list 2. And list 2 now has to move up because it just got connected to, and we don't want to reconnect to it again on accident. So list 2 is going to equal to list 2 next. And we're going to say that's pretty much it. Outside of these two if statements, we know that one of these either previous one next became list 1 or previous next became list 2, right? So one of them just got changed. So now we have to move previous, as in our pictures, we have to move previous to the last thing that it just got connected to. So we will say previous is equal to previous next. So that's done. But as we saw in our picture, we can still have leftover things in our in one of our linked lists. So in this case, L1 reached null, which broke this while loop. And we had these things left over. So what do? Well, we say, okay, we say previous next is going to equal this. So if there's no more list 1, if list 1 is null, we're going to just connect to list 2. Otherwise, we're going to connect to list 1. So basically all this notation says, like, if something in here is true, we're going to do this. Otherwise, we're going to do this. And we're basically setting the result into this. So we're saying, like, if list 1 is invalid or if list 1 is null, just connect it to list 2. Otherwise, if list 2 is a null pointer, connect it to the remnants of list 1. So we're going to do that. And the other thing we have to do, the thing we talked about, is we talked about severing this last connection. This connection right here from the temp head. So we're going to do return temp next to return the actual head. So now we can try to run this. And again, I made the same mistake where I called it L1. So I'll call it list 2, list 1. Okay, there we go. Run code. And there we go. It runs. We can submit. There we go. It's pretty fast. As for the runtime, it's, again, a linear runtime. But the difference with this is that we're only ever, no matter how big our lists are, the only two variables we're creating are this temporary node to have, like, to serve as a dummy head, and this previous node here that gets to, like, travel along as a pointer. And that's pretty much all there is to it. This solution is definitely a little bit trickier than the recursive one, but they both are pretty good. So yeah, cool.